So our special seminar speaker today is Dr. Jessica Oakes. And Jessica is from UC Berkeley. I was just told in Berkeley you have 10 minutes late time for any seminar they have. So I think today we're going to start on time. So before we getting Jessica started on her research seminar, we'll give a very quick introduction to our speaker. Jessica currently is a University of California presidential postdoc scholar at UC Berkeley. So I was told this is a very selective group of postdoc fellows representing the top 2% of postdoc population in the whole UC system. And she received a PhD in mechanical engineering from UC San Diego 3 years ago. And after completing her degree, Jessica performed a 1-year postdoc research in INRA in Paris, France. So she came to us with quite a bit of global perspective as well. And Jessica's research is combining, as you will tell from her research seminar, is flow dynamics, nanotechnology modeling with MRI imaging to look at a very specific lung biology problem with many translational implications. What impressed me is Jessica's work has been supported by a variety of fellowships and scholarships, all the way from NIH, from NSF, Whitaker Foundations, from INRIA postdoc grant. And recently, Jessica also received a prestigious American Lung Association grant to investigate the health effects of electronic cigarettes. So if you're a smoker, that will be a very interesting topic to hear Jessica talk about. So in the long term, Jessica is interested in merging engineering and medicine to diagnosis and optimize treatment of lung diseases. So we have a faculty member from lung biology group here from Dartmouth. I hope that will form very interesting potential collaborations. All right, so without further ado, I will give the floor to Jessica. Let's welcome our speaker.
Thank you. Thank you. I'm very excited to be here today to discuss with you my research in aerosols in the lung. Before I start in with the science, I just wanted to give you a little bit of personal information about me. I grew up in a town in Gasport, New York, which is somewhere situated between Buffalo, Niagara Falls, and Rochester. And the population there is about 1,000 people, so it's a tenth of the size of Hanover. So I'm used to the rural area. 7 million deaths per year worldwide are attributed to air pollution. Sources of air pollution include those from transportation sources, factory plants, and cook stoves. In addition, 1 in 5 deaths per year are attributed to cigarette smoking in the U.S., and they cause an economic burden of about $300 billion per year. These toxic particles not only cause respiratory diseases such as asthma, COPD, and cancer, but they can also cause cardiovascular diseases or whole body diseases. So this is a picture that I like to show of lungs. The one on the far left is of a healthy lung, and the one on the far right is of a 40-year-old coal miner, and the one in the middle is of a 90-year-old school teacher who probably lived in a city like Hanover or Gasport. And I hope you can appreciate what inhaling these toxic particles in their lung did to them over about 20 years of their lifespan. So the physics that make these particles dangerous can also be leveraged for inhaled aerosol medication. So aerosol medication, especially the very tiny particles, are an elegant and effective way to deliver therapeutics to the body. They can be used to treat pulmonary diseases such as asthma or cystic fibrosis, but they can also be used to treat whole body diseases, for example, insulin in diabetic patients. So the lung is a complex organ, which makes it very interesting to study. It's broken up into 3 parts. We have our mouth or extrathoracic airways, our conducting airways, and then the very deep regions of the lung called the respiratory zone. So in the mouth area, our Reynolds numbers are quite high, approaching around 3,000, so we will have turbulent or very best transitionally turbulent flow. At the trachea, which is generation 0, the lung keeps branching down, so our Reynolds numbers become smaller and smaller. So around 2,000, And then in the very deep regions of the lung, we have Reynolds numbers that are less than 1. So we have 3 different flow regimes that are happening in a single organ. To give you an idea of the size of our lung, the respiratory zone is about the size of a tennis court. So during respiration, we can think of it as a mechanical system. So during inspiration, our diaphragm contracts, which causes a negative pressure in our pleural cavity relative to atmosphere, which draws air into the lungs. During expiration, our muscles relax and the lung equalizes or becomes equilibrium. So this happens under about 10 centimeters of pressure of water. So if you can imagine a column of water about 10 centimeters, that's all the pressure that is needed to move our lungs throughout inspiration and expiration. So our lung is a very compliant system. So when we inhale particles in our lung, the destination of these particles is very dependent on the particle size. So for very small particles, which are less than 0.3 microns in diameter, in the nano-size regime, they're going to deposit in the very deep regions of the lung, and they're probably going to deposit due to Brownian diffusion. And these particles consist of tobacco smoke, for example, and automobile exhaust particles. And this is one of the reasons why tobacco smoke is so dangerous. In the mid-size range, about 1 micron in diameter, the particles will deposit due to sedimentation. So if you can imagine a stream flowing and you have a rock in it and it settles to the bottom, that's because gravity is acting on that rock, causing it to settle in that direction. So this occurs when the flow becomes pretty slow and the relative speed of the particle is greater than the relative speed of the surrounding fluid. And the last deposition mechanism is sedimentation. So this happens for relatively large particles greater than 5 microns, and this is when a particle will deposit at the bifurcation region due to its own inertia. Particles greater than 10 microns won't even deposit in the lung. They'll probably deposit in the air or in the nasal cavities. So lung dose imagery research is certainly an interesting area of study, whether we think about it on the toxic particle side or the aerosol medication side, but there are certainly some challenges for us to think about. First is there's huge inter- and intra-patient variability. So I'm different than you, and you're different than me, and also I'm different now than I was a few minutes ago how I'm breathing. There's little information about what happens on the organ level for sick patients, which leaves it an open area of study. It's challenging to translate to humans. So if we're doing in vitro cell culture type studies or animal studies, it's not a one-to-one correlation between what's happening in the laboratory and what's happening in humans. Long-term studies are very challenging. So looking at what happens over a person's lifespan or even person-to-person generation is an active area and open area research. One area that I'm particularly interested in is linking whole body organ level type research to cellular or biological response so we can look at the entire picture and also start to understand inflammation and remodeling of the airways. And finally, incorporating real particles. So much of our modeling methods have been developed assuming the particles are inert, they're perfect spheres, but that's not what happens in reality. So there's 4 types of ways that we can study aerosol dosimetry research. The first is using human aerosol exposure experiments. So this is when a subject will breathe in a well-defined aerosol bolus, so particles contained in air, and then they will exhale, and we can characterize this bolus based off the lung depth that they inhaled these particles, and then what happens to this bolus while exhaled. Well, this is a nice way to study particles. Obviously, we're only getting one story of the picture. We don't know where they actually went into the lung. We can use gamma scintigraphy or other imaging modalities to look at particles in the lung. This is a gamma scintigraphy 2D planar image. However, here we're exposing the people to radioactive material, so that is obviously undesirable, and we're only looking at coarse information. Alternatively, we can do animal exposure experiments, which are great because we can use in vivo measurements. We can do surgeries, we can do MRI, we can do SPECT CT on these animals. However, the correlation between animals and human is not one-to-one. And so what's happening in these animals is not necessarily what's happening in the general public. We can do 3D printed type in vitro models. So here is an example of a PIV setup. And this is work that came out of Stanford where we're doing PIV type MRI, where they're scaling the fluid to match Reynolds number and quantifying the flow field with MRI. We can also hook inhalers up to these models to look at deposition and test the efficiency of these inhalers. And while this is really giving us nice detailed deposition patterns, of course we're ignoring all biological response, and we're only looking at what happens to the particles once they deposit. The fourth way are computer simulations. So this here is a 1D representation of the total particle deposition versus particle diameter. We can make these idealized type geometries based off the average person, or we can do these 3D printed or 3D CT derived geometries. And these are great because we can get very detailed information. However, we often have to make assumptions, and it's hard to test these assumptions in their clinical setting. And we also have a huge need to validate these simulations. So I've been in this field for some time now and have made several contributions. To give you just a big picture, I worked on alveoli, so these are scaled up laboratory type experiments where I'm looking at PIV to quantify the flow field. I had the opportunity to go and visit a group at Technion in Israel, and we did these 3D acidized simulations. I've done animal experiments and collected airway morphometry, exposed animals to particles, MRI these animals. I also had the opportunity to fly animals on the zero gravity plane for NASA, and I didn't get sick, so good for me. And then I created these computer simulations and animal lungs, and now looking more at human lungs and differences between babies and adults. So today I'm going to mainly focus on the MRI experiments and then the computer simulations, but I'd be happy to answer any questions if you have them. Today I'll be talking a bit about emphysema. So emphysema is a chronic obstructive disease, and it impacts about 3.7 million people in the United States. There's no cure, and is typically caused by inhaling toxic particles over time. So here's an example of a normal alveolar sac, a cartoon, and you can see that the alveoli are very well defined. However, in the disease case, the septa in between the alveoli have been destroyed, so we have these ballooned air spaces. So what I was interested in is answering the question of, if we have emphysema, is particle retention enhanced or decreased in this population compared to healthy people? So the in vivo experiments, this is experiments that I did during my PhD at UCSD, was here where we created this aerosol exposure setup where we generated aerosols, sent them through a drying tube, and put them through the ventilator. The ventilator pushed particle-laden air into the rats, and then the rats passively exhaled. And so this happened for 40 minutes and less than a second per breath. So the rats breathed in quite a bit of aerosol particles. Half the rats had emphysema, and this was given to them with elastase treatment and waited 6 weeks for the disease to mature. Here I'm using superparamagnetic iron oxide particles. They're about 1 micron in diameter, so they're made of an iron core covered in plastic. The reason why I chose these types of particles was that I could quantify them with MRI later, which was the main goal of the study. So the second step is opening up the thoracic cavity. Because I'm using iron particles and I'm going to quantify the iron, I first needed to remove all the blood from the lungs, so I perfuse them and then excise them for the MRI. Before I make any conclusions about the particle deposition, I first need to make sure that I actually had emphysema. So I took nano-zoomer pictures of slices of the tissue. And what I'm showing here is healthy alveoli, where you can see well-defined spaces. And then the last days treated are the emphysematous rats, where these septa in between the alveoli were destroyed. To further quantify this, I quantified this destruction with MRI, and what I found, interestingly, was that the disease was mainly located at the bottoms of the diaphragmatic, the intermediate, and left lobe. And this is because when I gave the rats the emphysema, I held them like this, and their tails are pointed downwards. And I gave them the injection, and so that fell to the bottoms of the lung, and that's the areas of the lung that got the most of the disease. So here I quantified the particle deposition with MRI. I used a 3T scanner, a gradient echo sequence. Most of the imaging was taken between the hours of 12 a.m. and 4 a.m. because that's when the scanner was free. So here I'm having quantifying the single decay rate over time. So a voxel that contains a particle will have an enhanced signal decay rate because it destroys the MRI signal. And I can quantify that decay rate, and I can say that that is equal to 1 over the time constant of this decay. So I imaged this container as about the size of a tennis ball, and I had about 32 axial slices in this container, and each container contained about 3 lungs. Before I can actually quantify the particle, so before I showed you the signal decay, I needed to correlate this to the particle concentration. So here I have a calibration phantom where I have known amounts of particle concentrations in this phantom where I punched holes in it. And I found a linear correlation between the signal decay rate and the particle concentration, and I can use this as my calibration curve to quantify the particles. So this here is a typical MRI image that I get from the experiments. So there's 3 lungs. This one is not exposed to particles. These 2 are. And you can see just by eye that they're a little bit darker because of this enhanced signal decay rate. To orientate you, here's the heart, and I can identify each of the 5 lobes of the rat lung. So the rat has 1 left lobe and 4 right lobes. So interestingly, what I found, so this here is the concentration plots, where blue is no concentration and red is high concentration. What I found was that the elastase treated rat, or the emphysema rat, had more particles. And if I quantify that over each of the 5 lobes, what I find is that statistically there's more particles being retained in the diseased lungs compared to the healthy lungs. And this suggests that those emphysema may be more susceptible to airborne particles. However, this is a study where I was looking at rat lungs, and also this was only a mild case of emphysema, so what happens over the time period of emphysema is still quite unknown, but this is certainly a step in the right direction. So I collected this experimental data, and I knew there were some missing pieces that I wasn't going to be able to do experimentally, so I thought, why not do some computer simulations to try to uncover some of the mechanisms behind these results. So what I did was I designed these physiologically based multi-scale simulations that incorporate animal-specific geometry, experimental flow waveforms, animal-specific respiratory mechanics, and particles, I saw the Navier-Stokes equations for the fluid flow and the Maxey-Riley equation for the particles to look at flow in both the healthy and diseased lungs. So the first step in this system is to understand the total lung mechanics. And I can do that by assuming the lung can be described by this simple system where I have a resistor and a capacitor in series, where the resistance represents the resistance of the flow and the capacitor represents the compliance of the tissue. And I can represent that in circuit form with this simple ordinary differential equation. During my experiments, I measure the pressure over time, which I can use to solve this ordinary differential equation, where I search for a large parameter space for resistance and compliance and find the ones that uniquely match the solution. And what I found is that the compliance in the diseased lungs was 1.5 greater than in the healthy lungs, which is indicative of the disease, because in emphysema the compliance is destroyed and is increased. So if you think of an overstretched rubber band, when you stretch it back, it doesn't bounce back. That's because of its increased compliance. And the resistance remained the same. So this here is a solution. This is a volume over time. And for emphysema in healthy lungs, inhalation is exactly the same. And this is because my mechanical ventilator pushed the particle-laden air into the rats. And the ventilator settings were set exactly the same between the diseased and healthy rats. However, during exhalation, the movement was passive. So the rats exhaled on their own. And so here we can see that it takes longer for the diseased lungs to empty than the healthy lungs. So the second step is creating these image-based airway models. So this is MRI data of a rat lung. I had fluorocarbon in the airways and gadolinium in the tissue to create this nice contrast. And what I can do is draw path lines in the center of each of these airways. I could segmentate two-dimensional contours perpendicular to this path line and then loft them together to create these models. I can measure the models, the lengths, the diameters, the gravitational angles, and compare it to classical literature. And this can be done for any set of MRI, CT, etc. type images. The CFD analysis was done with an open source software that was first developed at Stanford, then at UCSD during my PhD by my professor Alison Marsden, and now she's back at Stanford, so it's back at Stanford again. But basically, it's an open source finite element software. I'm solving Navier-Stokes equations, assuming incompressible fluid, which is an okay assumption because my Mach numbers are quite small. I'm meshing the model. So this here is an initial mesh, and this is an adaptive mesh. And what I do is I adapt the mesh based off the gradient of the flow. So the mesh becomes quite finer near our boundary layers because it's adapted where the gradients are high. And this is really important when we're looking at these types of irregular type geometries. I think one of the most important parts of these types of simulations is how we define boundary conditions. So we can measure the trachea flow rate at the flow rate or the pressure at the trachea, but we cannot measure those values or those parameters at each of these outlets. It's completely infeasible right now with current technology. So we have to make assumptions to prescribe the boundary conditions. So what we can do is take the resistance compliance network that I showed you a couple of slides ago and prescribe that at each one of these outlets. And I can parameterize these resistance and compliances based off the load volume in the cross-sectional area, and assuming that these are proportional to those measurements. Of course, as more experimental data becomes available, we can parameterize them even better. I can model the disease airways by taking the information I gathered from the MRI that showed that the disease was mainly located at the bottoms of these 3 lobes. I can increase the compliance in these airways to represent the disease. So this here, I'll show you the flow field. First we'll do inspiration and then expiration. The flow field is shown here. So inspiration, the flow rate is quite steady, and then expiration, we have this initial high peak flow rate, and this is because the mechanical ventilator is pushing the system, and then the system is being released, and it empties very quickly. This is showing you a healthy and diseased lung, and from where you're sitting, you're probably saying they look exactly the same. The only thing that is different is that the flow rate to the areas that are diseased are higher because the compliance is higher. But if I take a more detailed viewpoint, what I can look at is the differences between the two parts of the lung. So in the healthy lung, what's interesting is the lung expands and contracts in symmetry. However, in the diseased lung, the areas that contain the disease, in this case the bottom parts, are finishing expanding after the healthy parts because of the differences in time constants. And so it happens at this very small time, we have air still being inhaled to the diseased regions and then exhaled from the healthy regions. And this is just a minor form of the disease. Of course, if we had a more severe form of the disease, this may even happen even more, which causes air trapping, which causes disease acceleration. So the next step after we have this flow field is to look at the particle transport. So I'm doing Lagrangian particle tracking, which means I'm tracking each individual particle in the flow field. I'm solving a reduced form of the Maxey-Riley, which is basically modeling the drag of the particle, so the difference between the flow speed and the particle speed, and then the gravitational settling of the particle. I'm releasing particles proportional to the local flow rate. So in the times where the flow rate is higher, if you're thinking of a flow rate in each of a little tiny element, more particles are going to be released. And this is just keeping a constant flux of particles coming in throughout the whole cycle. I'm modeling 1 micron diameter particles so that I can match my experiments as closely as possible. So this here movie is showing you the particle released during inspiration. So the particles are being released at the trachea, and they have two options. They can deposit on the wall of the airways, or they can exit downstream. So the gravity is into the board because the rat is laying on its back, and about 2% of particles deposit, and they mainly deposit at the bifurcation regions and the areas where the flow may become chaotic. And these simulations show that while total deposition wasn't quite different between the healthy and emphysema, there was more deposition in these localized areas here because more air is going to those regions, so more particles are going to those regions, so more particles can deposit. So the next part is where I want to compare these results back to the experimental data. So here I'm going to plot the circles, which is the experimental data. So this is the normalized number of particles depositing for each of the 5 lobes of the rat. And then the squares are the numerical predictions. And what I'm finding is that with my model, I'm able to relatively accurately predict what's happening in the lung. This is for the healthy lung. Except for these 2 lobes, the apical lobe and the cardiac lobe, which is really interesting because the apical lobe in the literature, especially the toxicology literature, is considered the dirty lobe. It's the one that gets all the junk. But I'm unable to reproduce that with my simulations, which is going to motivate some of my next work. In the diseased lungs, I was unable to predict what's happening in these 2 specific lobes. And this is because I'm ignoring all parts of the lung. So while the geometry I showed you is quite complex, it's only about 3 or 4% of the total lung volume. So I'm ignoring all the alveoli, all the small airways. And if I included that, then perhaps I can understand more what's happening. So while these simulations do include animal specific geometry, flow waveforms, respiratory mechanics. I'm not answering is what happens to these particles once they leave the domain. And if you notice that particles are only going in one direction, so I'm not modeling exhalation. So it was interesting because I went to a conference about a year ago and I was talking to some of the clinicians, and they had two schools of thought. The first was that no particles deposit during exhalation, and the second one was that inspiration, expiration are completely the same. So from an engineering's perspective, I thought perhaps this is not the truth, because not only is inspiration, expiration flow waveforms are quite different, but if you imagine a particle being released at the top, the geometry that that particle will see will be completely different if a particle is released in this direction. So I thought this was a great opportunity for me to explore this area as a modeler. The challenge, though, is it's not straightforward, which is the reason why it hadn't been done before, is knowing what happens to all these particles once they leave. And this requires passing of information between 3D and 1D domains. So I came up with a solution where I have this three-dimensional model here connected to one-dimensional models. And these one-dimensional models, which are called the trumpet models, represent all airways downstream of this model. And by coupling these lower dimensional models to these three-dimensional models, I don't need to simulate the whole lung in full, which is impossible right now with current computational power and probably not needed. But we can answer this question by passing this information. The challenge here is in the 3D domain, we're tracking each individual particle. And the 1D domain, we're looking at a concentration approach. So we kind of have to switch to coordinate system, so to speak, between the two domains. So this 1D trumpet model is basically a model that represents all airways in the bronchioles. So each generation we have more and more airways. So we have this trumpet type model because the sum of all those airways in that generation becomes bigger and bigger. So that's how we can assume it's a trumpet. We have this bronchial cross-section area, and then we have this area added because of the alveoli, and this area can expand and contract. So we can determine the flow in these airways by solving a mass or volume conservation equation. And for the particle transport, we can solve a convection diffusion model. So this is the same equation that you may see in heat transfer, but it's parameterized specifically for this work. So here we have the effective diffusion term, which models the particles coming together because each airways are different. And then we have the convection term, which is the main transport term in this model. So this is what's driving the particles in the lung. And then we have a loss term, which models deposition. And this loss term can be described based on analytical formula or empirical formula. One of the second challenges in doing this is defining the 1D airway geometry. So luckily for me, in the 70s and 80s, someone took a cast lung of a rat and measured all 2 to the 23 power number generation airways, the length, diameters, gravity angles, and such, which I can use for my models. And they have published that online for anyone to use. And what I have is the cross-sectional area for each generation, and it's dependent on the lobe. So for example, the apical lobe, which is considered the dirty lobe, reaches the acinar generation, so that's where we become these alveoli, at a much shorter distance than, for example, some of the other lobes. These airways expand and contract based off the flow rate that I feed it and the volume conservation law. So when I pass information between the 3D and 1D domains, this here is for inspiration. So here I'm releasing particles and they exit. And so I release particles here, and because the particles are pretty inert and the model's pretty short, they exit the model quite quickly. And so that concentration becomes quite constant throughout the whole inspiration. But during expiration, when I'm passing information from the 1D to the 3D, at first it's quite constant, but then it quickly becomes close to, starts to get very small. And this is because the lung didn't completely fill in. So some of those particles deposited, so there's less to be exhaled, and because the lung didn't fill in, once the lung empties, there's no more particles to be exhaled. So here I'm going to show you a video of inhalation. So particles again are being released here, and then they're passed to these 1D models. I'm plotting here the normalized concentration versus airway generation. So a value of 1 would indicate that the lung was completely filled in. Okay, I'm sorry. It says my PowerPoint counted an error and needs to quit. Oh, thank you. Please don't quit. It's quitting. I'm so sorry. Now you guys are going to see my chalk talk. I think it's the videos. It has a hard time sometimes, but that's really weird. So the next video I'm going to show you is expiration. No. I think it's okay. I think it was delayed. So expiration is when particles from the 1D domain is being passed to the 3D domain. And you can see that I color-coded them based off their lobe that they're originating from, so there's some mixing going on. Also, the lung doesn't completely empty, so there's particles that remain still in the lung, and those can deposit in the next breath. Please work. Okay. Yay, so this is deposition patterns in the 3D domain for inspiration. So most of the particles, so gravity is outside the board. So most of the particles are depositing at these bifurcation regions. I'm plotting the concentration. So a value of red or pink is going to be high concentration. White is no particles. Blue is low concentration. So this is inspiration. And then this is expiration. And they're completely different. And this is because during expiration, we have this peak flow rate, which is causing high vorticity near the wall. So the particles are swirling and hitting the wall during expiration, which they're not doing during inspiration. Also, the particles are not depositing at these bifurcation regions like inspiration because inertia is not acting on them in the same way as they did during inspiration. So that's what the 3D looks like. If I look at the entire lung, where purple is inspiration and gray is expiration, about 2 times more particles deposit during inspiration than expiration, mainly because most of the particles are exhaled quite quickly from the lung, and then also because inertia is not having such a big role during expiration. Also, you notice this bar here for the apical lobe is a bit higher than the rest of the lobes. And this is because the deposition efficiency is a bit higher in this lobe. And that's because that lobe reaches the acinar region at a shorter distance than the other lobes. And once the airways reach the alveoli, deposition is enhanced because there's more surface area for them to deposit on. So here is the light blue is the acinar region, and dark blue is the conducting airways. And so you can see that more particles are deposited in that region, so that the path length is shorter to that region, then deposition will be higher. If there was, if someone was taking a deeper breath, more particles would deposit in that region. If I compare back to the experimental data, again, the squares are the experimental data. If I'm looking at only the 3D simulation, I'm not matching very well to the experimental data. But if I have the 3D, 1D coupling, so essentially I'm taking in lobe-specific deposition efficiency, having a much better comparison to my experimental data. So you say, well, Jessica, that's great. That's for rats. So what happens in humans? So what I did was I started this study about 6 months ago where I'm looking at deposition in human airways. So this model is of a 36-year-old woman created from CT images. And first thing you can note between the rat and the human, notice these aren't to scale. That would be a really scary rat. Sorry. So what we have is very small airways and the rat coming from these big airways. So it's called monopodal branching. And in the human airways, we have more dichotomous branching, so we have a more even split. So because I mechanically ventilated the rat, I wanted to also mechanically ventilate my human so I have a direct comparison. Oh, sorry. So while the deposition was about the same between the rat and the human, about 2%, if you notice, my rat model is much more extensive than my human model. So if I was able to have images of better resolution, I can certainly create more airways and do more of a comparison. What was interesting, though, was that in the rat, it was more uniformly distributed at the back of the model, but in the human, it was more distributed at the bifurcation region. So because Stokes number is higher in the human model, inertia is higher, and so we have more particles depositing at these bifurcation regions. If I do my 3D, 1D coupling, what I find, so this is a human versus the rat. So a value of 1 would say that rat and human had the same deposition, total deposition for different particle sizes, but this isn't true. For very small particles, more particles are depositing in the rat versus the human, but the opposite is true for the human, so it's not a simple scaling. And if I look at the regional deposition where I'm plotting the alveoli zone, or the bronchial zone normalized by the alveoli zone, there was a greater fraction of particles deposited in the acinar zone of the rats than the humans. So if I'm doing toxicology studies or pharmaceutical studies in the rat, but more particles are deposited in the areas of the rat that get translated to the bloodstream, obviously this information is going to probably skew our results, and so it's not a direct one-to-one comparison, so caution should be made. And the final thing that I wanted to show you that I'm really excited about, which is going to motivate some of my future work, is what about kids? So luckily I had this collaboration with a clinician at Stanford who gave me about 50 data sets of CT images. He's a heart doctor, so he has thoracic cavity CT images from a 3-month-old to a 77-year-old. And what I could do is create these models. So this is a 3-month-old baby. The trachea diameter is 0.5 centimeter, so it's very tiny. And this is of an adult airways, and so this trachea diameter is about 2 centimeters. One thing that is interesting, not only the geometry differences, but the ventilation differences. So during humans, our volume change is about 20%. But the tidal volume, so that's the inhale volume that you take, versus FRC, which is your resting volume, is much greater in the baby. So the lungs are expanding and contracting more, and they're using more of their lungs than we do as an adults. So what does this have on particle deposition? So here I'm just showing you one particle size. This is more like pilot data in the adult versus the baby. And the baby is much more susceptible to airborne particles than the adult is, mainly because of this enhanced ventilation, but also because these airways are much smaller, so there's less of a distance for the particle to travel to hit the wall. So this is really interesting. However, in the adult, because fewer particles are depositing, more particles can be delivered downstream, so perhaps there's more deposition downstream. So this isn't the end of the story, it's just the beginning. So I know I've talked about many subjects today, so I just wanted to leave you with some take-home messages. The first is we can quantify particles in the lung with MRI. So here I use iron particles, but we can go into gadolinium particles. We can use ultra-short echo time. So this was a first step in that direction. My experiments showed that those with emphysema may be more susceptible to airborne particles. I'm assuming this is happening because of air trapping and the particles have more time to sediment and deposit. These physiologically based simulations can provide novel insight beyond the resolution of experimental data. They can also motivate experiments. They can also optimize on experiments. They can save money. They're not going to replace experiments, but it certainly can be coupled with experiments to advance science at a fast rate. If we're modeling inhalation, exhalation, we must take into account what's happening downstream, either with these 1D models or perhaps more sophisticated models in the future. Coupling this 3D, 1D resulted in better comparison with the experiments because each lobe acts differently. If we're looking at disease cases, sometimes the disease is only located in one area of the lung. So taking in this lobe-specific information is crucial. Translation from animals to humans is not simple, and it definitely depends on particle size, the respiration parameters. But modeling can certainly be helpful in this area. My preliminary simulation suggests that children may be more susceptible to airborne particles, which should be taken into consideration. And finally, validation is really necessary and important when we consider these types of simulations for clinical translation. So with that, I would like to thank you for your attention and introduce you to some of the people that were instrumental in this work. These are my PhD advisors, the PhD group. This is a group in France, and this is a group at Berkeley. Our PI takes us out for dinner every time someone has their first publication. So thank you, and I would be happy to answer any questions. Yeah, certainly. So in my future work, I hope to work on asthma and optimizing drug delivery, mainly because with asthmatic patients, they only retain about 10 to 20% of the inhaled particles, and most of those particles are going to the healthy airways, not to the disease airways, so there's certainly room to optimize drug delivery. We could also think about inhaled chemotherapy for lung cancer patients so we can directly target the tumor. I think there's a lot of areas that we can go into, for sure.
Very interesting talk, fascinating materials. I was wondering about water in the air, the implications of air as it goes into the lung.
Mm-hmm.
Whether the surfaces of those airways are wet or mucus, and whether that needs to be taken into account in these models or not. What your thoughts are on water and mucus?
Yeah, that's a good question. I always say that to questions it's hard to answer. No, I'm just kidding. So that's, it is a great question. So I don't take into the account of the mucus. Once the particles leave the domain, I assume, or hit the wall, I assume they deposit. What happens to those particles once they deposit is a great question to try to answer. Especially when we're thinking of bronchitis, where we have increased mucus production, and cystic fibrosis, where we have mucus problems. And I think my intuition, because the airway sizes are so much smaller, because of this mucus, we're going to have a lot more particles depositing.
Ask Professor Diamond's question a little bit differently, or maybe ask a related question. So the humidity in the lung environment is going to be different than the humidity in the ambient air. Is that enough to change the diameter of particles as they're passing through the lung? And how might you imagine that would affect deposition?
Yeah, so in my future research, I want to look more at e-cigarettes. I'm starting some of that data simulation framework now. But based off the relative humidity that these e-cigarettes are taken, if the air is dry and we have a very humid environment, the particle sizes are going to change. And so that is going to impact deposition because deposition is mainly dependent on the particle size. On the other hand, if we started off with small particles and somehow they grew in the lung, then perhaps we can bypass these upper airways because the particles are small enough they're not going to deposit due to inertia. But once they reach the bottoms of the lung, then they can deposit because they grew. So taking this into account is, I think, where some of this research is headed.
Another question that might relate to Sal's question is what happens when you cough?
Yeah, that would be a fantastic modeling problem. During coughing, we have our airways probably collapse a bit. So depending on how aggressive that cough is, I don't think anyone has considered modeling cough. I think there's a group at MIT that's thought about sneezing, just because it's a really challenging computational problem. Because you can imagine we have turbulent flow, so it would certainly be interesting to study it for sure. I was interested in airway collapse because I think that's a really awesome, like a mechanical fundamental problem to study, but I haven't explored it yet.
Other questions? On the back, yeah, good. Have you looked into optimizing waveforms of ventilators to basically optimize drug delivery? Going that route?
Yeah, so I recently submitted a proposal to the Burroughs Wellcome Fund on optimizing drug delivery. And so I am working on creating a optimization framework, which I can optimize the particle size, maybe the shape, the carrier gas composition, because we can use heliox, for example, the respiration waveforms, the time that the particles are released. And I hope that this someday can lead to translation and perhaps designing smart inhalers or patient-specific inhalers, especially for very challenging cases.
In your simulations, what's the criteria for the particle deposition? Like, does it have to hit the wall with a certain speed? You know, if it just erases the wall, does it, would you say it's stuck there? Or just imagine the particles are going to hit the trachea at some point on the way down. It would just be hard to not. If it just needs to touch it, wouldn't they all deposit it?
Yeah, so I mean, first answer the first part of your question. So once they hit the wall, I assume they deposit. They don't have to hit the wall at a certain speed. I don't consider bounce or anything like that. I assume because the airways are covered in mucus that they're kind of sucked in. Because the flow rate in the trachea is quite fast, actually the particles don't have time to sediment to deposit on the trachea, typically, because the relative speed of the particle is much smaller than the speed of the flow.
Yeah, I have one more question just about the validation concept for this type of scale modeling. So intelligence are really key, especially for like multiple length scales. So you're sort of have flow over different regimes, and I was wondering could you just comment on how you would like validate individual mechanisms of how you incorporate things like surface tension effects or compliance effects at the really small scale while you're sort of measuring empirically in humans something like just going in and out. You know, how do you inform the mechanics over different length scales with your simulations and experiments?
Yeah, so I mean, maybe this is where like laboratory, like 3D printed or compliant type models can come in. There's some MRI or SPECT CT work that's being done in humans, I think at MIT, so that would be, and also with my collaboration at Air Liquide. So it's really hard to validate these models. That's why we're starting with the animals. But yeah, especially look at different length scales and different time scales. Because if you can think about it, if you consider growth remodeling, it's completely different time scales. there's so much to do. It's really exciting.
So quick question on the particles. The particle dimension you specifically point out is 3 microns, as the environmental impact here at 0.5 and so forth. So in terms of the distribution particle size, and can you model with scalable to describe the distribution of various types of particles in this deposition with the lung tissue?
Yeah, for different particle sizes, it's not a problem to model those. For large particles, inertia is going to take into account. For very small particles, we're going to have Brownian diffusion. And so I'm working on adding Brownian diffusion into some of my codes now. To look at a mixture of particles, I think to have numerical convergence, you're probably going to have to simulate different particle sizes and then add that together somehow, because the solution is very sensitive to the number of particles being released, so you need about 17 million particles to be released, which is much higher than the concentration that's in the ambient air, for example.
And I think Jessica will stay here one more day, so you're welcome to utilize this very informal setting. Let's thank our speaker again.